Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The concept of mineral hardness, which refers to the resistance of a mineral specimen to being scratched or abraded by another material, has been a subject of systematic investigation for well over 2 centuries. Though informal observations about the relative hardness of different stones and metals undoubtedly extend much further back into the history of human engagement with the natural world. The ability to distinguish harder materials from softer ones would have been of immediate practical importance to the earliest toolmakers, who needed to select stones that could hold a sharp edge and resist wear, and to the earliest metalworkers, who needed to understand how different metals and alloys behaved under stress. The most widely known and most commonly used scale of mineral hardness is the one devised by the German mineralogist Friedrich Mohs, who published his system in 1822 in a work titled Treatise on Mineralogy. Mohs's scale consists of 10 reference minerals, arranged in order of increasing hardness, with each mineral being capable of scratching all those below it in the sequence and being scratched by all those above it. The 10 minerals, in order from softest to hardest, are talc, gypsum, calcite, fluorite, apatite, orthoclase feldspar, quartz, topaz, corundum, and diamond. Each mineral is assigned a hardness number from 1 to 10, with talc being 1 and diamond being 10. It is important to note that the Mohs scale is an ordinal scale, not a ratio or interval scale. This means that the numerical values assigned to the minerals indicate only their relative order of hardness, not the actual magnitudes of their hardness. The difference in absolute hardness between corundum, which has a Mohs hardness of 9, and diamond, which has a Mohs hardness of 10, is far greater than the difference between any other pair of adjacent minerals on the scale. In quantitative terms, as measured by indentation hardness tests, diamond is approximately 4 times harder than corundum, while the differences between the lower-numbered minerals are considerably smaller. This nonlinearity is a significant limitation of the Mohs scale for scientific purposes, though it remains perfectly adequate for the practical purpose of mineral identification in the field. Talc, the softest mineral on the Mohs scale, is a hydrous magnesium silicate with the chemical formula Mg3C4010OH2. It has a hardness of 1, meaning it can be scratched by virtually any other mineral and even by a fingernail, which has a hardness of approximately 2.5 on the Mohs scale. Talc forms in metamorphic environments, typically through the alteration of magnesium-rich minerals, such as olivine and pyroxene, in the presence of water and carbon dioxide. It has a characteristically greasy or soapy feel, which gives rise to its common name, soapstone, when it occurs in massive form. Talc has been used by humans for thousands of years, both as a carving material and as an ingredient in cosmetics and personal care products. The ancient Egyptians used talc as a component of eye makeup, and ground talc, commonly known as talcum powder, has been widely used as a body powder since at least the 19th century. Gypsum, the second mineral on the Mohs scale, is a hydrated calcium sulfate with the chemical formula CaSO4 multiplied by 2H2O. It has a hardness of 2, which means it can be scratched by a fingernail. Gypsum is one of the most abundant evaporite minerals, forming through the evaporation of seawater or saline lake water in arid environments. It occurs in a variety of forms, including the translucent, platy crystals known as selenite, the fibrous variety known as satin spar, and the fine-grained massive variety known as alabaster. Alabaster has been prized as a carving material since antiquity, and some of the most beautiful examples of ancient Egyptian and Mesopotamian sculpture were carved from this delicate stone. Gypsum is also the principal ingredient of plaster of Paris, which is produced by heating gypsum to approximately 150 degrees Celsius to drive off some of the water of crystallization, yielding the hemihydrate form CaSO4 multiplied by 1/2 H2O. When the hemihydrate is mixed with water, it rehydrates and sets into a hard, solid mass, a property that has been exploited for centuries in construction, sculpture, and medicine. Calcite, the third mineral on the Mohs scale, is calcium carbonate, CaCO3, and it is one of the most common and widely distributed minerals on the surface of the Earth. It has a hardness of 3, meaning it can be scratched by a copper coin, but not by a fingernail. Calcite is the principal component of limestone, marble, and chalk, and it is also the primary mineral in the shells and skeletons of many marine organisms, including corals, mollusks, foraminifera, and coccolithophores. The crystal structure of calcite belongs to the trigonal crystal system, and calcite crystals exhibit a remarkable optical property known as birefringence, or double refraction, in which a single ray of light entering the crystal is split into 2 rays that travel through the crystal at different speeds and in slightly different directions. This property was first described by the Danish scientist Rasmus Bartholin in 1669 and was later explained by Christian Huygens using his wave theory of light. Fluorite, the 4th mineral on the Mohs scale, is calcium fluoride, CaF2, and it has a hardness of 4. Fluorite is notable for its wide range of colors, which include purple, blue, green, yellow, orange, pink, and colorless, as well as for its tendency to fluoresce under ultraviolet light. Indeed, the phenomenon of fluorescence takes its name from fluorite, having been first described in detail in a specimen of this mineral by the British scientist George Gabriel Stokes in 1852. Fluorite typically forms in hydrothermal veins, often in association with metallic ore minerals such as galena and sphalerite, and it is found in significant deposits in many parts of the world, including China, Mexico, South Africa, and the United Kingdom. The principal industrial use of fluorite is as a flux in steel making, where it is added to the blast furnace charge to lower the melting point of the slag and improve its fluidity, a practice that gives fluorite its alternative name, fluorspar. Apatite, the 5th mineral on the Mohs scale, is a group of phosphate minerals with the general formula Ca5, PO4, 3, F, ClOH. The most common member of the group is fluorapatite, Ca5PO4, 3F, which has a hardness of 5. Apatite is of particular biological significance because it is the principal mineral component of vertebrate bones and teeth. Hydroxyapatite, Ca5PO4, 3OH, constitutes approximately 70% by weight of bone and approximately 97% by weight of tooth enamel, making it by far the most abundant mineral in the human body. The total mass of apatite in an adult human skeleton is approximately 2.5 kilograms. Apatite is also an important source of phosphorus for the fertilizer industry and large deposits of sedimentary phosphorite, which is composed primarily of microcrystalline apatite, are mined in several countries, including Morocco, China, and the United States. Orthoclase feldspar, the sixth mineral on the Mohs scale, is a potassium aluminum silicate with the chemical formula KAlC3O8. It has a hardness of 6, which places it in the middle of the range between the softest and hardest naturally occurring minerals. Orthoclase is one of the most abundant rock-forming minerals, occurring as a major constituent of granite, syenite, and many other igneous and metamorphic rocks. It is also a common component of Arkose sandstone, a type of sedimentary rock that forms from the erosion of granite and related rocks. The name orthoclase derives from the Greek words orthos, meaning straight, and klausis, meaning breaking, referring to the mineral's characteristic cleavage, which produces fragments that meet at right angles or very nearly so. Orthoclase feldspar is used in the manufacture of ceramics, glass, and porcelain, where it serves as a flux to lower the melting temperature of the silica component. Quartz, the seventh mineral on the Mohs scale, is silicon dioxide, SiO2, and it is the second most abundant mineral in the Earth's continental crust, after the feldspars. Quartz has a hardness of 7, which makes it harder than most common materials and harder than the blade of a typical steel knife, which has a Mohs hardness of approximately 5.5 to 6.5. Quartz occurs in an extraordinary variety of forms and colors. The transparent, colorless variety is known as rock crystal, and it has been prized as a gemstone and ornamental material since antiquity. The purple variety, colored by trace amounts of iron and natural irradiation, is known as amethyst and has been valued as a gemstone for thousands of years. Other varieties of quartz include citron, which is yellow to orange, smoky quartz, which is brown to black, rose quartz, which is pink, and milky quartz, which is white and translucent. Microcrystalline varieties of quartz include chalcedony, agate, jasper, and flint, each of which has played an important role in human material culture. The piezoelectric properties of quartz, which were discussed earlier in the context of quartz clocks and watches, have made it an indispensable material in modern electronics. A properly cut and oriented quartz crystal vibrates at a precise and stable frequency when an alternating electrical voltage is applied to it, and this property is exploited in a vast range of devices, from wristwatches and clocks to radio transmitters, frequency filters, and computer oscillators. The worldwide demand for high-quality quartz crystals for electronic applications far exceeds the natural supply, and the majority of quartz crystals used in electronics are now produced synthetically by the hydrothermal method, in which silica is dissolved in a hot, pressurized alkaline solution and deposited on seed crystals over a period of several weeks. The global production of synthetic quartz crystals amounts to several thousand tons per year. Topaz, the eighth mineral on the Mohs scale, is an aluminum silicate fluoride hydroxide with the chemical formula Al2CO4 FOH2. It has a hardness of 8, making it one of the hardest naturally occurring silicate minerals. Topaz occurs in a range of colors, including colorless, yellow, orange, pink, blue, and, rarely, green. The most prized variety is Imperial Topaz, which displays a rich orange to reddish-orange color and is found primarily in the Ouro Preto region of Minas Gerais, Brazil. Blue topaz, which is extremely popular in the contemporary jewelry market, is typically produced by irradiating and heat-treating colorless or pale topaz, a process that was developed in the 1970s and has since become standard practice in the gem trade. Natural blue topaz does occur, but is quite rare and usually of a much paler color than the treated material. Corundum, the ninth mineral on the Mohs scale, is aluminum oxide, Al2O3, and it has a hardness of 9. Corundum is the third hardest natural material, after diamond and moissanite, and its extreme hardness makes it an important industrial abrasive. Synthetic corundum, produced by the Verneuil flame fusion process developed by Auguste Verneuil in 1902, is manufactured in large quantities for use as an abrasive in grinding wheels, sandpaper, and other applications. The gem varieties of corundum are among the most valuable of all gemstones. Ruby, which is corundum colored red by trace amounts of chromium, has been prized for its beauty and rarity for thousands of years. Sapphire, which encompasses all non-red gem varieties of corundum, is most commonly blue, colored by trace amounts of iron and titanium, but also occurs in pink, yellow, orange, green, and colorless varieties. The finest rubies, known as pigeon blood rubies for their intense, slightly purplish red color, are found in Myanmar and command prices that can exceed those of equivalent-sized diamonds. Diamond, the 10th and hardest mineral on the Mohs scale, is pure carbon crystallized in the cubic crystal system under conditions of extreme temperature and pressure. Diamond has a hardness of 10, and no naturally occurring material can scratch it. The extraordinary hardness of diamond is a consequence of its crystal structure, in which each carbon atom is bonded to 4 neighboring carbon atoms by strong covalent bonds arranged in a tetrahedral geometry, creating a three-dimensional network of exceptional rigidity and strength. The conditions necessary for the formation of natural diamonds, temperatures of at least 1,000 degrees Celsius and pressures of at least 4.5 gigapascals, exist at depths of approximately 150 to 200 kilometers below the Earth's surface within the upper mantle. Diamonds are brought to the surface by deep-seated volcanic eruptions that produce a type of rock known as kimberlite, named after the town of Kimberley in South Africa, where it was first identified in 1871. The history of diamond mining and the diamond trade is a lengthy and often troubled narrative that has shaped the economies and politics of several nations, particularly in southern and central Africa. The discovery of diamonds at Kimberley in 1866 and the subsequent rush of prospectors to the region led to the establishment of several large mining companies, the most prominent of which was De Beers Consolidated Mines, founded by Cecil Rhodes in 1888. De Beers came to dominate the global diamond market for much of the 20th century, controlling an estimated 80 to 90% of the world's rough diamond supply at its peak. The company maintained high prices for diamonds through a combination of supply management, stockpiling, and aggressive marketing, including the famous advertising campaign launched in 1947 with the slogan "A diamond is forever," which was instrumental in establishing the diamond engagement ring as a cultural norm in the United States and subsequently in many other countries. Beyond the Mohs scale, several other hardness scales have been developed for more precise and quantitative measurements of material hardness. The Vickers hardness test, developed in 1921 by Robert L. Smith and George E. Sandland at Vickers Limited in the United Kingdom, measures the indentation hardness of a material by pressing a square-based diamond pyramid into the surface under a known load and measuring the size of the resulting indentation. The Vickers hardness number is calculated by dividing the applied load by the surface area of the indentation, and the test can be applied to a wide range of materials, from soft metals to extremely hard ceramics. The Vickers hardness of talc is approximately 1, while the Vickers hardness of diamond is approximately 10,000. Illustrating the enormous range of hardness values that the Mohs scale compresses into its 10 ordinal categories. The Knoop hardness test, developed in 1939 by Frederick Knoop and his colleagues at the National Bureau of Standards in the United States, is similar in principle to the Vickers test, but uses an elongated, rhombus-shaped diamond indenter rather than a square-based pyramid. The Knoop indenter produces a shallower, more elongated impression than the Vickers indenter, making it particularly suitable for testing thin coatings, brittle materials, and materials with pronounced directional variation in hardness. The Knoop hardness of diamond varies with crystallographic direction, ranging from approximately 5,700 to 10,400 kilograms per square millimeter, reflecting the anisotropy of the diamond crystal structure. The Rockwell hardness test, developed by Stanley P. Rockwell in 1914 and patented in 1919, differs from the Vickers and Knoop tests in that it measures the depth of indentation rather than the size of the indentation. The Rockwell test uses either a diamond cone or a hardened steel ball as the indenter, depending on the material being tested, and applies a series of loads in a prescribed sequence. The Rockwell hardness number is calculated from the net depth of the indentation, and the test is widely used in industry because of its speed, simplicity, and the fact that the indentation is small enough to be considered non-destructive for many applications. Several different Rockwell scales exist, designated by letters such as A, B, and C, each using a different combination of indenter geometry and applied load, and the choice of scale depends on the material being tested. The Brinell hardness test, which predates all of the other indentation hardness tests, was developed by the Swedish engineer Johann August Brinell in 1900. The Brinell test presses a hardened steel or tungsten carbide ball, typically 10 millimeters in diameter, into the surface of the test material under a known load, and the hardness is calculated from the diameter of the resulting indentation. The Brinell test was the first widely accepted method for the standardized measurement of material hardness, and it remains in common use for testing metals, particularly those with coarse or uneven microstructures, for which the smaller indenters used in the Vickers and Knoop tests might give unrepresentative results. The physical mechanisms underlying the hardness of minerals are intimately connected to the nature of the chemical bonds that hold the atoms of the mineral together and to the arrangement of those atoms in the crystal lattice. In general, minerals with strong covalent bonds, in which electrons are shared between adjacent atoms, tend to be harder than minerals with ionic bonds, in which electrons are transferred from one atom to another, and much harder than minerals held together by weaker van der Waals forces or hydrogen bonds. The hardness of a crystal also depends on the density of bonds per unit volume, which is related to the packing efficiency of the crystal structure and on the presence or absence of weak planes along which the crystal can be deformed or cleaved. Diamond, as noted earlier, owes its extraordinary hardness to the three-dimensional network of strong carbon-carbon covalent bonds that permeates its crystal structure. Each carbon atom in diamond is bonded to 4 neighbors in a tetrahedral arrangement, and the carbon-carbon bond in diamond has a bond energy of approximately 347 kilojoules per mole, which is among the strongest single bonds known in chemistry. The compact, tightly bonded structure of diamond leaves little room for the movement of dislocations, the line defects in the crystal lattice that are the primary mechanism by which most crystalline materials deform plastically. And this resistance to dislocation movement is the fundamental physical basis of diamond's hardness. Graphite, which is the other common crystalline form of pure carbon, provides an illuminating contrast to diamond. In graphite, the carbon atoms are arranged in planar sheets, with each atom bonded to 3 neighbors within the sheet by strong covalent bonds. The sheets themselves, however, are held together by weak van der Waals forces, and they can slide over one another with very little resistance. This easy sliding of the graphite layers gives graphite a Mohs hardness of only 1 to 2, despite the fact that the covalent bonds within each layer are extremely strong. The difference in hardness between diamond and graphite, 2 materials composed of the same element, is thus entirely a consequence of the different arrangements of atoms in their respective crystal structures. The relationship between crystal structure and hardness is further illustrated by the case of boron nitride, which exists in 2 principal crystalline forms hexagonal, and cubic. Hexagonal boron nitride has a layered structure similar to that of graphite, with alternating boron and nitrogen atoms arranged in planar sheets, and it has a similar softness, with a Mohs hardness of approximately 1 to 2. Cubic boron nitride, by contrast, has a three-dimensional tetrahedral structure analogous to that of diamond, with alternating boron and nitrogen atoms, and it is the second hardest known material after diamond, with a Vickers hardness of approximately 4,500 to 5,000 kilograms per square millimeter. Cubic boron nitride is manufactured synthetically and is widely used as an industrial abrasive, particularly for the grinding and cutting of ferrous metals, for which diamond is unsuitable because carbon reacts with iron at high temperatures. The concept of hardness is more complex than it might initially appear, encompassing several distinct but related physical properties. Scratch hardness, which is what the Mohs scale measures, is the resistance of a material to being scratched by a harder material. Indentation hardness, which is what the Vickers, Knoop, Rockwell, and Brinell tests measure, is the resistance of a material to localized plastic deformation under the pressure of a hard indenter. Rebound hardness, measured by the Shore scleroscope and the Lieb hardness tester, is the height to which a standard weight bounces after being dropped onto the surface of the material. While these three types of hardness are generally correlated, they are not identical, and the ranking of materials can differ depending on which type of hardness is being measured. The hardness of minerals is influenced not only by their crystal structure and chemical bonding, but also by a variety of other factors, including temperature, pressure, the presence of impurities, and the state of crystallographic perfection. Most minerals become softer at elevated temperatures, as the increased thermal energy of the atoms facilitates the movement of dislocations and other defects. The hardness of quartz, for example, decreases from approximately 1,100 Vickers hardness units at room temperature to approximately 600 at 500 degrees Celsius. Conversely, the hardness of most materials increases with increasing pressure, as the compression of the crystal lattice makes it more difficult for dislocations to move. The presence of impurity atoms in the crystal lattice can either increase or decrease the hardness of a mineral, depending on the nature and concentration of the impurities. In many metals and alloys, the addition of small amounts of impurity atoms, a process known as solid solution hardening, significantly increases hardness by impeding the movement of dislocations. In minerals, impurities can have more variable effects. For example, the hardness of corundum is not significantly affected by the small amounts of chromium that give ruby its red color, or the iron and titanium that give sapphire its blue color, because these trace impurities substitute for aluminum in the crystal lattice without significantly distorting its structure. The study of mineral hardness has applications that extend well beyond the identification and classification of minerals. In materials science and engineering, hardness testing is one of the most widely used methods for characterizing the mechanical properties of materials because it is simple, quick, and can be performed on small samples with minimal preparation. Hardness data are used to predict the wear resistance, machinability, and fatigue life of metals, ceramics, and polymers, and hardness testing is a routine part of quality control in manufacturing. In geology and planetary science, the hardness of minerals provides information about the conditions under which rocks formed and the forces that have acted upon them over geological time. The hardness of the mineral grains in a sedimentary rock, for example, influences the rate at which the rock erodes, and the relative hardness of different minerals determines which minerals survive the weathering process and which are destroyed. The development of superhard materials, defined as materials with a Vickers hardness exceeding 40 gigapascals, is an active and commercially important area of materials research. Diamond, with a Vickers hardness of approximately 70 to 150 gigapascals, depending on the direction and quality of the crystal, remains the hardest known material. However, several other materials approach or rival diamond in hardness under certain conditions. Aggregated diamond nanorods, also known as hyperdiamond, which consist of interlocking nanoscale diamond crystallites, have been reported to have a hardness exceeding that of single crystal diamond. Wurtzite boron nitride and lonsdaleite, a hexagonal form of carbon found in meteorites, have been predicted by theoretical calculations to be even harder than diamond, though these predictions have not been conclusively verified by experiment. The synthesis of artificial diamond, first achieved on a reproducible basis by General Electric in 1955, has made diamond widely available for industrial applications at a cost far below that of natural gem-quality diamond. Industrial synthetic diamonds are produced by two principal methods. The high-pressure, high-temperature method subjects graphite to pressures of approximately 5 to 6 gigapascals and temperatures of approximately 1,400 to 1,600 degrees Celsius in the presence of a metal catalyst, causing the graphite to transform into diamond. The chemical vapor deposition method grows diamond films on a substrate from a carbon-containing gas, such as methane, which is decomposed by a hot filament or a plasma discharge. The worldwide production of synthetic industrial diamond amounts to several billion carats per year, vastly exceeding the production of natural diamond, and synthetic diamonds are used in a wide range of cutting, grinding, drilling, and polishing applications. The application of hardness measurements to gemology has resulted in the development of specialized testing methods adapted to the particular requirements of the gem trade. Gemologists use hardness as one of several diagnostic properties for identifying gemstones, though they must be careful to avoid damaging valuable specimens in the process. The scratch test, in which a mineral of known hardness is drawn across an inconspicuous surface of the specimen, is sometimes used for rough identification, but it is generally avoided for cut and polished gemstones because of the risk of damage. Instead, gemologists rely primarily on non-destructive methods such as refractive index measurement, specific gravity determination, and spectroscopic analysis, supplemented by visual observation of color, luster, and crystal habit. The Mohs scale, despite its age and its acknowledged limitations, remains in active use today, particularly in field geology and in introductory geology courses, because of its simplicity and the ready availability of the reference materials. A geologist working in the field can perform a rough hardness test using nothing more than a fingernail, which has a Mohs hardness of approximately 2.5, a copper coin, which has a hardness of approximately 3.5, a steel knife blade, which has a hardness of approximately 5.5 to 6.5, and a piece of quartz, which has a hardness of 7. These simple tools, combined with the ability to perform scratch tests between the unknown mineral and the reference materials, are sufficient to narrow down the identity of most common minerals and to provide a useful starting point for more detailed laboratory analysis. The history of mineral hardness measurement, from Friedrich Mohs's original 10-mineral scale to the sophisticated nanoindentation instruments of the 21st century, mirrors in microcosm the broader history of scientific measurement. Each advance in technique has revealed new complexities and subtleties in the concept of hardness itself, challenging the simplifying assumptions of earlier methods and demanding new theoretical frameworks to explain the observed phenomena. The seemingly simple question of how hard is this mineral turns out, upon close examination, to involve considerations of atomic bonding, crystal structure, defect mechanics, temperature, pressure, strain rate, and testing geometry, each of which must be taken into account for a complete and accurate characterization. The ongoing effort to understand and measure mineral hardness with ever greater precision and sophistication is, in this sense, a testament to the enduring human drive to quantify and comprehend the material world, one careful measurement at a time. The measurement of hardness at the nanoscale, using a technique known as nanoindentation, has opened new avenues of investigation in materials science and mineralogy that were entirely inaccessible to the macroscopic hardness tests of earlier eras. Nanoindentation instruments, which became commercially available in the 1980s, use a diamond-tipped indenter, typically with a Berkovich geometry, which is a three-sided pyramid, to make indentations with depths measured in nanometers, billionths of a meter, and loads measured in millinewtons or even micronewtons. The indentation depth and the applied load are continuously recorded during both the loading and unloading phases of the test, producing a load displacement curve from which the hardness and the elastic modulus of the material can be calculated. The Oliver Farr method, developed by Warren Oliver and George Farr in 1992, is the most widely used analytical procedure for extracting mechanical properties from nanoindentation data. The method is based on the observation that the initial portion of the unloading curve, which represents the elastic recovery of the material as the indenter is withdrawn, can be fitted by a power law function, and that the contact area at the moment of peak load can be inferred from the fitting parameters. The hardness is then calculated as the peak load divided by the contact area and the elastic modulus is calculated from the slope of the unloading curve at the point of maximum displacement. The Oliver Farr method has been applied to a vast range of materials, from metals and ceramics to biological tissues and thin films, and it has become the standard method for nanomechanical characterization in both academic research and industrial quality control. The ability to measure hardness at the nanoscale has revealed that the hardness of many materials varies with the depth of indentation, a phenomenon known as the indentation size effect. In most crystalline materials, the measured hardness increases as the indentation depth decreases, a behavior that is attributed to the strain gradient that develops beneath the indenter. At very small indentation depths, the strain gradient is steep, and the resulting geometrically necessary dislocations, which are additional dislocations that must be present to accommodate the shape change caused by the indenter, contribute to an enhanced resistance to further deformation. The Nix-Gao model, proposed by William Nix and Huajian Gao in 1998, provides a theoretical framework for understanding the indentation size effect in terms of the interaction between geometrically necessary dislocations and statistically stored dislocations. The hardness of minerals at the nanoscale can differ significantly from the values measured at the macro scale, and nanoindentation has been used to investigate the micromechanical properties of individual mineral grains within polycrystalline rocks, the mechanical behavior of mineral surfaces, and the effects of weathering and alteration on mineral hardness. For example, nanoindentation studies of feldspar grains in granite have shown that the hardness of the grain interiors is significantly higher than that of the grain boundaries and of zones affected by chemical weathering, providing quantitative data on the mechanisms of rock weathering and erosion. The concept of hardness has also been extended to materials that are not conventionally regarded as minerals. The hardness of biological materials such as tooth enamel, bone, nacre, and insect cuticle has been studied extensively using both conventional and nanoindentation techniques. Tooth enamel, which is composed primarily of hydroxyapatite crystals arranged in bundles of prisms approximately 5 micrometers in diameter, has a Vickers hardness of approximately 300 to 400 kilograms per square millimeter, comparable to that of many engineering ceramics. The hardness of enamel varies with location within the tooth, being greatest at the outer surface and decreasing toward the enamel dentin junction, a gradient that is thought to be an adaptation for resisting the stresses of mastication. Nacre, the iridescent material that lines the inner surface of many mollusk shells and forms the outer coating of pearls, is a remarkable example of a biological composite material that achieves a combination of hardness and toughness far exceeding that of its mineral constituent alone. Nacre is composed of thin, hexagonal platelets of aragonite, a polymorph of calcium carbonate, approximately 0.5 micrometers thick and 5 to 10 micrometers in diameter, separated by thin layers of organic matrix composed of proteins and polysaccharides. The Vickers hardness of nacre is approximately 200 to 300 kilograms per square millimeter, which is similar to that of monolithic aragonite. However, the fracture toughness of nacre, which is a measure of its resistance to crack propagation, is approximately 3,000 times greater than that of monolithic aragonite, a dramatic enhancement that is attributed to the layered microstructure, which forces cracks to follow tortuous paths along the interfaces between the platelets. The development of computational methods for predicting the hardness of materials from first principles, without the need for experimental measurement, has been an important recent advance in materials science. Density functional theory calculations can be used to compute the elastic constants, ideal shear strengths, and other mechanical properties of crystalline materials from knowledge of their crystal structure and chemical composition alone. Several empirical and semi-empirical models have been proposed for predicting hardness from computed properties. The Chignot model, for example, relates the Vickers hardness of a material to the ratio of its shear modulus to its bulk modulus and to the value of its shear modulus, providing a simple but remarkably effective predictor of hardness for a wide range of materials. The search for new super-hard materials, driven by the needs of the cutting tool, drilling, and abrasive industries, continues to be an active area of research. Carbon nitride, with the hypothetical composition C3N4 and a crystal structure based on that of beta-silicon nitride, was predicted in 1989 by Marvin Cohen and Amy Liu to have a hardness approaching or exceeding that of diamond. This prediction stimulated extensive experimental efforts to synthesize carbon nitride, but the results have been mixed, with most synthesized samples falling well short of the predicted hardness. Other candidate superhard materials include rhenium diboride, osmium diboride, and various boron-rich compounds, each of which has been the subject of both theoretical predictions and experimental investigations. The industrial applications of hardness measurements and hard materials are vast and varied. Diamond and cubic boron nitride cutting tools are used in the machining of metals, ceramics, and composites. Diamond drill bits are essential for geological exploration, mining, and oil and gas drilling. Abrasive diamond and alumina powders are used in the precision grinding and polishing of optical lenses, semiconductor wafers, and gemstones. Hardness testing is a routine part of quality control in the manufacture of steel, aluminum alloys, ceramics, and many other materials. The wear resistance of engine components, bearings, and cutting tools is directly related to their hardness, and the selection of appropriate materials for these applications depends critically on accurate and reliable hardness data. The story of mineral hardness, from Moses elegant but qualitative scale to the quantitative precision of modern nanoindentation, is a story of scientific progress driven by both intellectual curiosity and practical necessity. The simple act of scratching one mineral against another, which served the mineralogists of the early 19th century as a reliable method of identification, has evolved into a sophisticated branch of materials science that draws on crystallography, solid-state physics, computational chemistry, and precision engineering. Yet the fundamental question remains the same as it was in Moses' day. How does one material resist being marked by another? And what determines the relative ease with which different materials can be scratched, dented, or worn away? The answer, as we have seen, involves the interplay of atomic bonding, crystal structure, defect mechanics, and testing conditions. And the effort to understand this interplay in ever greater detail continues to yield insights that are both scientifically fascinating and practically valuable. The minerals that Friedrich Mohs selected for his scale in 1822 remain, after more than 2 centuries, the standard reference points for hardness in geology and mineralogy. Talc, gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, and diamond, these 10 minerals, spanning the full range of natural hardness from the softest to the hardest, continue to serve as the benchmarks against which all other minerals are compared. The scale that bears Mohs's name is a monument not only to his own careful observations, but also to the broader tradition of systematic mineralogy that flourished in the universities of Central Europe in the early 19th century. It is a tradition that valued precision, classification, and the patient accumulation of empirical knowledge, and it is a tradition whose influence continues to be felt in every geology classroom and every geological field camp around the world. Wherever a student picks up a piece of rock and reaches for a copper coin or a steel knife blade to determine, by the simple and ancient method of scratching, how hard the minerals within it are. The relationship between mineral hardness and the geological environments in which minerals form provides a rich area of study that connects the physical properties of individual minerals to the broader processes of rock formation, metamorphism, and weathering that shape the Earth's crust. Minerals that form under conditions of high temperature and high pressure, such as those found deep within the Earth's crust or upper mantle, tend to be harder than minerals that form at lower temperatures and pressures near the surface. This general trend reflects the fact that high-pressure conditions favor the formation of densely packed crystal structures with short, strong interatomic bonds, which are the structural characteristics most closely associated with high hardness. The relationship between formation conditions and hardness can be observed across the Mohs scale. Talc and gypsum, the 2 softest minerals on the scale, form at relatively low temperatures and pressures. Talc forms during the metamorphism of magnesium-rich rocks at temperatures typically below 500 degrees Celsius, and gypsum forms through the evaporation of seawater at surface temperatures. Calcite and fluorite, with Mohs hardnesses of 3 and 4, form across a wider range of conditions, but are commonly found in sedimentary and low-temperature hydrothermal environments. At the upper end of the scale, corundum forms at high temperatures in aluminum-rich, silica-poor environments, typically in contact metamorphic zones or in igneous rocks such as syenite. Diamond, the hardest mineral, forms at the extreme conditions of temperature and pressure found in the upper mantle at depths exceeding 150 kilometers. The weathering resistance of minerals, which is strongly correlated with their hardness, determines which minerals survive the processes of erosion and sediment transport and which are destroyed. This principle is formalized in the concept of the Goldic dissolution series, proposed by Samuel Goldic in 1938, which arranges the common rock-forming silicate minerals in order of their resistance to chemical weathering. The order of the Goldic series is approximately the reverse of the Bowen reaction series, which describes the order in which silicate minerals crystallize from a cooling magma. Minerals that crystallize at high temperatures, such as olivine and pyroxene, are the least resistant to weathering, while minerals that crystallize at lower temperatures, such as quartz and muscovite, are the most resistant. The correlation between weathering resistance and hardness is not perfect because chemical weathering depends on factors other than hardness, such as the solubility of the mineral's constituent ions and the stability of its crystal structure in the presence of water and dissolved acids. Nevertheless, the general trend is clear, and the dominance of quartz in beach sands and river sediments around the world is a direct consequence of its combination of high hardness and chemical stability. The hardness of minerals also plays an important role in the formation of placer deposits, which are concentrations of dense, hard, and chemically resistant minerals in stream beds, beaches, and other sedimentary environments. Placer deposits form when the combined effects of gravity, flowing water, and wave action separate heavier and harder minerals from lighter and softer ones. Gold, platinum, cassiterite, which is tin oxide, magnetite, ilmenite, rutile, zircon, and various gemstones including diamond, sapphire, and ruby are among the minerals most commonly found in placer deposits. The survival of these minerals in the harsh environment of a stream bed or beach, where they are subjected to continuous abrasion by sand and gravel, is a testament to their hardness and durability. The gemological significance of hardness extends beyond the identification and classification of gemstones to encompass practical considerations of durability and wearability. A gemstone intended for use in a ring, which is subject to frequent contact with hard surfaces and abrasive particles, must have a hardness of at least 7 on the Mohs scale to resist scratching and maintain its polish over years of daily wear. This criterion effectively limits the choice of durable ringstones to quartz and harder materials, including topaz, beryl, which includes emerald and aquamarine, chrysoberyl, which includes alexandrite, spinel, corundum, which includes ruby and sapphire and diamond. Softer gemstones, such as opal, with a Mohs hardness of 5.5 to 6.5, turquoise, with a hardness of 5 to 6, and pearl, with a hardness of 2.5 to 4.5, are better suited to earrings, pendants, and brooches, which are less exposed to abrasion. The phenomenon of directional variation in hardness, known as hardness anisotropy, is observed in many minerals and provides additional information about the relationship between crystal structure and mechanical properties. In kyanite, an aluminum silicate mineral with the formula Al2CO5, The hardness varies from approximately 4.5 along the length of the crystal to approximately 7.0 across its width. A variation so pronounced that kyanite is sometimes called the two-hardness mineral. This dramatic anisotropy arises from the arrangement of aluminum-oxygen bonds in the crystal structure, which are more closely spaced and more difficult to break in the direction perpendicular to the crystal's elongation than in the parallel direction. Diamond also exhibits significant hardness anisotropy, a fact that has been known to gem cutters for centuries, and that is essential to the art of diamond cutting and polishing. The hardness of diamond varies with both the crystal face and the direction of scratching on a given face. The octahedral faces of a diamond crystal, which correspond to the atomic planes with the highest density of carbon atoms, are harder than the cubic faces, and within each face, certain directions are harder than others. Diamond can only be polished by another diamond, and the gem cutter must orient the polishing direction to take advantage of the softer directions on the surface being worked. The traditional knowledge of diamond cutters, accumulated over centuries of practice and passed down from master to apprentice, includes an intimate understanding of these directional variations in hardness. Even though the cutters themselves may not have expressed this knowledge in the language of crystallography. The hardness of geological materials at the scale of whole rocks, as opposed to individual mineral grains, depends not only on the hardness of the constituent minerals, but also on the texture and fabric of the rock, including the sizes, shapes, and arrangements of the mineral grains, the nature of the grain boundaries, and the presence or absence of porosity and microcracks. A rock composed entirely of quartz grains, such as a well-cemented quartzite, will have a scratch hardness close to that of quartz itself, approximately 7 on the Mohs scale. A limestone composed of calcite grains will have a scratch hardness close to that of calcite, approximately 3. However, a granite, which is composed of grains of quartz, feldspar, and mica, each with different hardness values, will exhibit a complex pattern of scratching behavior that depends on which mineral grain the indenter encounters. The abrasiveness of rocks and soils, which is a measure of their ability to wear away the surfaces of tools and machinery that come into contact with them, is directly related to the hardness of their mineral constituents. The Searcher Abrasiveness Index, developed by the Centre d'études et recherches de Charbonnage de France, is a widely used measure of rock abrasiveness that involves dragging a steel stylus across a freshly broken rock surface under a standard load and measuring the amount of wear on the stylus tip. The Searcher Index is correlated with the quartz content and the hardness of the hardest mineral grains in the rock, and it is used extensively in the tunneling and mining industries to predict the rate of wear on cutting tools and drill bits. The measurement of hardness in extraterrestrial materials, including meteorites, lunar samples, and the surfaces of planets and asteroids explored by robotic spacecraft, has provided valuable information about the composition and geological history of other bodies in the solar system. Meteorites, which are fragments of asteroids, the Moon, and Mars that have fallen to the Earth's surface, contain a wide variety of minerals, many of which are also found in terrestrial rocks, but some of which are unique to the extraterrestrial environment. The mineral moissanite, which is silicon carbide, SiC, was first identified in a meteorite by Henri Moissat in 1893 and has a Mohs hardness of 9.25, placing it between corundum and diamond. Natural moissanite is extremely rare on Earth, but is thought to be more common in the carbon-rich envelopes of certain types of stars, and it has been detected in interstellar dust grains and in the atmospheres of carbon-rich asymptotic giant branch stars. The robotic exploration of Mars has included several instruments designed to assess the hardness and mechanical properties of Martian rocks and soils. The rock abrasion tool carried by the Mars exploration rovers Spirit and Opportunity, which landed on Mars in January 2004, was designed to grind away the outer, weathered surface of rocks to expose fresh interior surfaces for analysis by other instruments. The rate at which the rock abrasion tool ground through different rocks provided qualitative information about the hardness and abrasiveness of the target materials. More recent Mars missions, including the Mars Science Laboratory rover Curiosity and the Mars 2020 rover Perseverance, have carried percussion drilling systems that provide additional data on the mechanical properties of Martian rocks. The investigation of mineral hardness continues to evolve as new experimental techniques and theoretical frameworks are developed. The advent of in situ nanoindentation, in which hardness measurements are performed inside a scanning electron microscope or a transmission electron microscope, allows researchers to observe the deformation mechanisms directly at the nanoscale while simultaneously measuring the applied force and displacement. These observations have revealed a rich variety of deformation phenomena, including dislocation nucleation, phase transformations, and amorphization, that occur beneath the indenter during hardness testing and that contribute to the measured hardness in ways that were previously inaccessible to direct observation. The field of computational materials science has made it possible to simulate the indentation process at the atomic level using molecular dynamics calculations. In these simulations, the positions and interactions of millions of individual atoms are tracked as a virtual indenter is pressed into the surface of a virtual crystal, allowing the mechanisms of deformation and the pathways of dislocation motion to be observed with a resolution and completeness that is impossible to achieve experimentally. Molecular dynamics simulations of nanoindentation in diamond, for example, have revealed that the onset of plastic deformation beneath the indenter involves the nucleation of dislocations on specific crystallographic planes, and that the critical load for dislocation nucleation depends on the crystallographic orientation of the surface being indented, in good agreement with experimental observations of hardness and isotropy. The ongoing study of mineral hardness, spanning more than 2 centuries of systematic investigation and drawing on disciplines as diverse as mineralogy, solid-state physics, mechanical engineering, and computational science, exemplifies the cumulative and self-correcting nature of scientific inquiry. Each generation of researchers has built upon the work of its predecessors, refining methods, extending the range of materials studied, and deepening the theoretical understanding of the physical mechanisms underlying hardness. Friedrich Mohs, working with nothing more than a set of carefully chosen reference minerals and the simple technique of the scratch test, established a framework for comparing the hardness of different materials that has proven remarkably durable and useful. The researchers of today, armed with nano-indentation instruments, synchrotron X-ray sources, and supercomputers, continue the work that Mohs began, seeking to understand, with ever greater precision and depth, the deceptively simple question of why some materials are harder than others. The historical context within which Friedrich Mohs developed his hardness scale is worth examining in some detail, as it sheds light on the intellectual traditions and practical concerns that shaped early 19th century mineralogy. Mohs was born in 1773 in Gernrode, in what was then the Principality of Anhalt-Bernburg, and he studied at the University of Halle and later at the renowned Mining Academy in Freiburg, Saxony, where he was a student of Abraham Gottlob Werner, one of the most influential mineralogists of the era. Werner had developed a system of mineral classification based primarily on the external characteristics of minerals, including color, luster, crystal form, cleavage, and hardness. And Mohs built upon this tradition by developing a more systematic and reproducible method for comparing the hardness of different mineral species. Werner's approach to mineralogy, which emphasized careful observation and systematic description over chemical analysis, was a product of the intellectual culture of late 18th century Germany, where the Romantic movement's emphasis on direct experience of nature intersected with the practical needs of the mining industry. The silver, tin, and iron mines of Saxony and neighboring regions were major economic assets, and the ability to identify minerals accurately and quickly in the field was of considerable commercial importance. Werner's students, who included not only Mohs, but also Alexander von Humboldt, Leopold von Buch, and many other influential geologists and mineralogists, spread his methods and his influence throughout Europe and the Americas. Mohs's hardness scale was first published in 1822 in his Grundriss Mineralogie, or Treatise on Mineralogy, and it quickly gained acceptance as a practical and reliable method for comparing the hardness of different minerals. The 10 reference minerals that Mohs selected for his scale were chosen because they were readily available, relatively common, and because they provided a reasonably even spacing across the range of natural hardness values. It is worth noting that the spacing of the Mohs scale is not intended to be uniform, and Mohs himself was well aware that the differences in hardness between adjacent minerals on the scale were not equal. The scale is purely ordinal, and its value lies in its simplicity and reproducibility rather than in any quantitative precision. The choice of diamond as the upper reference point on the Mohs scale was natural, given that diamond was already recognized as the hardest known substance. The ancient Greeks knew that diamond could scratch any other material, and the name diamond itself is derived from the Greek word adamus, meaning unconquerable or invincible, a reference to the mineral's superlative hardness. The choice of talc as the lower reference point was equally natural, as talc was widely recognized as one of the softest minerals, easily scratched by a fingernail and possessing a characteristic greasy feel that distinguished it from all other common minerals. The intermediate minerals on the Mohs scale were selected to provide convenient reference points across the range of hardness values encountered in common minerals. Gypsum, calcite, fluorite, and apatite were chosen because they were common, easily obtainable, and because their hardness values were well established through practical experience. Orthoclase feldspar, quartz, topaz, and corundum were chosen for similar reasons, with the additional consideration that they represented important rock-forming minerals or economically valuable gemstones. The practical procedure for performing a Mohs hardness test is straightforward, but requires some care and experience to perform accurately. The basic method involves attempting to scratch the unknown mineral with each of the reference minerals in turn, beginning with the softest and working upward. If the reference mineral scratches the unknown mineral is softer than the reference. If the unknown mineral scratches the reference is harder. If neither mineral can scratch the other, they have approximately the same hardness. In practice, several complications can arise. Some minerals have a tendency to leave a mark on a harder surface that can be mistaken for a scratch, but is actually a streak of powder deposited by the softer mineral. This can be distinguished from a true scratch by wiping the surface clean and examining it under magnification. Some minerals have different hardness values on different crystal faces or in different directions, as noted earlier in the case of kyanite, and this can lead to apparently contradictory results if the tester is not aware of the possibility. The use of common objects as hardness references is a convenient extension of the Mohs method that is particularly useful in field geology, where the 10 reference minerals may not always be at hand. A fingernail has a Mohs hardness of approximately 2.5, a copper coin approximately 3.0 to 3.5, a glass plate approximately 5.5, a steel file approximately 6.5, and a streak plate, which is a piece of unglazed porcelain approximately 6.5 to 7.0. These common object references, combined with the 10 standard reference minerals, provide a practical toolkit for rapid mineral identification in the field. The persistence of the Mohs scale in an age of far more precise and sophisticated hardness testing methods is a testament to the value of simplicity in scientific measurement. The scale requires no specialized equipment, no electrical power, and no training beyond a basic understanding of the scratch test procedure. It can be applied in any environment, from a well-equipped laboratory to a remote field camp, and it yields results that are immediately interpretable and universally understood. For the working geologist in the field, the Mohs scale remains an indispensable tool, as useful today as it was when Friedrich Mohs first proposed it more than 200 years ago. The broader significance of mineral hardness as a physical property extends to considerations of planetary formation and differentiation. The processes by which the Earth and other rocky planets separated into a dense metallic core, a silicate mantle, and a relatively thin crust are governed in part by the mechanical properties of the minerals involved, including their hardness, their elastic moduli, and their resistance to plastic deformation at the temperatures and pressures prevailing deep within a planetary interior. The flow of the solid mantle, which drives plate tectonics and the convective removal of heat from the Earth's interior, occurs by the slow plastic deformation of mantle minerals, principally olivine and its high-pressure polymorphs, under the influence of thermal convection. The rate of this flow is determined by the viscosity of the mantle, which is itself related to the ease with which dislocations can move through the crystal lattices of the constituent minerals. The hardness and mechanical properties of minerals under extreme conditions of temperature and pressure are studied using high-pressure experimental techniques, including the diamond anvil cell, in which a small sample is compressed between the flat faces of two diamond anvils to pressures that can exceed those found at the center of the Earth. The use of diamond in this application exploits both its extreme hardness, which prevents the anvils from deforming under the applied pressure, and its transparency to a wide range of electromagnetic radiation, including visible light and X-rays, which allows the sample to be studied spectroscopically and crystallographically while under pressure. The diamond anvil cell has been used to study the mechanical properties of minerals at pressures exceeding 300 gigapascals, corresponding to conditions found deep within the interiors of giant planets such as Jupiter and Saturn. The intersection of mineral hardness research with materials engineering has produced numerous practical innovations. Cemented carbides, also known as hard metals, are composite materials consisting of particles of tungsten carbide, WC, embedded in a matrix of metallic cobalt. The tungsten carbide particles, which have a Vickers hardness of approximately 2,000 kilograms per square millimeter, provide extreme wear resistance, while the cobalt matrix provides toughness and resistance to fracture. Cemented carbides were first developed in Germany in the 1920s and have since become the dominant material for cutting tools, mining drill bits, and wear-resistant components. The worldwide market for cemented carbides is estimated at approximately $15 billion per year, underscoring the enormous economic importance of hardness as a material property. The development of thin, hard coatings, applied by physical vapor deposition or chemical vapor deposition to the surfaces of cutting tools and other components, represents another important application of hardness science. Coatings of titanium nitride, tin, which has a Vickers hardness of approximately 2,000 to 2,500 kilograms per square millimeter, titanium aluminum nitride, diamond-like carbon, and other hard materials are routinely applied to cutting tool inserts to extend their useful life by factors of 3 to 10 or more. The golden color of titanium nitride coatings is a familiar sight on drill bits end mills, and other cutting tools available in hardware stores and machine shops around the world. The quiet, methodical science of mineral hardness, with its careful measurements and its patient accumulation of data, stands as an example of the kind of sustained, incremental scientific work that often lacks the glamour of more dramatic discoveries, but that forms the essential foundation upon which technological progress is built. From the earliest scratch tests of Friedrich Mohs to the nanoscale investigations of 21st century materials scientists, the study of hardness has been driven by the same fundamental questions. What makes one material harder than another? How can we measure hardness accurately and reproducibly? And how can we use our understanding of hardness to design and select materials for the countless applications that depend on resistance to wear, abrasion, and deformation? These questions, simple as they may sound, have occupied some of the finest minds in mineralogy, physics, and engineering for more than 2 centuries, and the answers that have been found, while impressively detailed and nuanced, continue to invite further investigation and refinement. The story of mineral hardness is, in the end, a story without a conclusion, a continuing conversation between the scientist and the material world, conducted one careful scratch at a time. The cultural and artistic dimensions of mineral hardness have shaped human civilization in ways that extend far beyond the purely scientific or industrial. The relative hardness of different stones determined which materials could be carved, polished, and fashioned into tools, jewelry, and architectural elements, and the aesthetic qualities of polished hard stones have been valued by virtually every culture in recorded history. The art of gem cutting, which depends entirely on the exploitation of differences in hardness between the abrasive and the stone being cut, has a history extending back at least 3,000 years. To the earliest seal stones and intaglios of ancient Mesopotamia and Egypt. The ancient Mesopotamians, working primarily with softer stones such as lapis lazuli, with a Mohs hardness of approximately 5 to 5.5, carnelian, with a hardness of approximately 6.5 to 7, and jasper, with a hardness of approximately 6.5 to 7, developed sophisticated techniques for cutting and engraving gemstones using abrasive powders of corundum, known in its granular form as emery, and later diamond dust. The earliest known gem engravings, dating to approximately 3,500 BCE, are cylinder seals from Sumer, which are small, cylindrical stones engraved with intricate scenes that could be rolled across wet clay to produce a continuous impression. The production of these seals required not only artistic skill, but also an understanding of the relative hardness of the seal material and the abrasive being used to cut it. An understanding that was presumably acquired through generations of practical experience rather than through any formal theory of mineral hardness. The Romans developed the art of gem cutting to a high level of refinement, producing cameos and intaglios of extraordinary delicacy and beauty. The cameo, in which a raised image is carved from the lighter-colored upper layer of a banded stone such as sardonyx or agate, requires particular skill because the carver must remove material from around the image without damaging the delicate relief. The hardness of agate, approximately 7 on the Mohs scale, made this work extremely challenging, requiring the use of diamond-pointed tools and abrasive slurries of corundum or garnet suspended in oil. The finest Roman cameos, such as the Gemma Augustea, which dates to approximately 9 to 12 CE and depicts the Emperor Augustus in a scene of imperial triumph, represent an extraordinary combination of artistic vision and technical mastery of hard materials. The art of diamond cutting, which is among the most specialized and demanding of all lapidary arts, has its origins in India, where diamonds have been mined and valued for at least 2,000 years. The ancient Indians recognized that diamond could be cut and polished only by other diamonds, and they developed techniques for cleaving diamonds along their natural crystal planes and for polishing the resulting surfaces using diamond powder mixed with oil on a rotating wheel. The art of diamond cutting spread to Europe in the late Middle Ages, and by the 15th century, the cities of Bruges, Antwerp, and Amsterdam had become major centers of the diamond cutting industry. The development of the brilliant cut, which is the most common faceting style for diamonds today, was a gradual process that extended over several centuries. The earliest diamond cuts were simple polished surfaces on natural crystal faces, known as point cuts. In the 15th century, the table cut was developed, in which the point of an octahedral diamond crystal was ground flat to create a large, flat table facet. The rose cut, featuring a flat base and a dome-shaped crown covered with triangular facets, appeared in the mid-16th century. The modern round brilliant cut, with its 57 or 58 precisely angled facets designed to maximize the return of light to the viewer's eye, was developed in the early 20th century. With Marcel Tokowski's 1919 treatise Diamond Design providing the theoretical basis for the optimal proportions and angles. The technology of polishing hard stones, which is intimately connected to the science of mineral hardness, has evolved continuously from ancient times to the present. The basic principle of polishing is the removal of material from a surface by abrasion, using progressively finer abrasive particles until the scratches produced are too small to be detected by the eye or by touch. The finest polished surfaces on hard gemstones have a surface roughness of approximately 1 nanometer, or 1/1,000,000th of a millimeter. A level of smoothness that approaches the theoretical limit set by the spacing of individual atoms in the crystal lattice. The abrasive materials used in polishing have evolved along with the understanding of mineral hardness. Natural abrasives, such as emery, which is a mixture of corundum and magnetite, and garnet, which has a Mohs hardness of 6.5 to 7.5, were used for thousands of years before the development of synthetic abrasives in the late 19th and early 20th centuries. Synthetic aluminum oxide, produced by the Bayer process from bauxite ore, was first manufactured commercially in the 1890s and quickly became the dominant abrasive for metalworking and surface finishing. Silicon carbide, First synthesized by Edward Acheson in 1891 and marketed under the trade name carborundum, has a Mohs hardness of approximately 9.25 and is used for grinding and polishing harder materials, including glass, ceramics, and some metals. The production of synthetic diamond abrasives, beginning in the 1950s, revolutionized the cutting and polishing of the hardest materials. Synthetic diamond powder, available in a range of precisely controlled particle sizes from tens of micrometers down to a few nanometers, is used for the precision polishing of optical components, semiconductor wafers, hard ceramics, and gemstones. The development of polycrystalline diamond compact, or PDC, cutting elements in the 1970s combined the extreme hardness of diamond with the toughness of a sintered tungsten carbide substrate, creating a cutting tool that was ideally suited for the drilling of oil and gas wells in hard rock formations. PDC drill bits now account for the majority of the drilling footage in the global oil and gas industry, and their performance is directly attributable to the exceptional hardness of the diamond cutting layer. The science of tribology, which is the study of friction, wear, and lubrication, is closely related to the science of mineral hardness and draws extensively on hardness data in the analysis of wear processes. The rate at which a material wears when in sliding contact with another material is governed by a number of factors, including the relative hardness of the two materials, the applied load, the sliding speed, the surface roughness, and the presence or absence of lubricants. Archard's wear equation, proposed by John Frederick Archard in 1953, states that the volume of material removed by wear is proportional to the sliding distance and the applied load and inversely proportional to the hardness of the softer material. This simple relationship, while not universally applicable, provides a useful first approximation for the prediction of wear rates in many engineering applications. The hardness of geological materials plays a crucial role in the science of sedimentology and in the interpretation of sedimentary environments. The shape and roundness of sedimentary grains, which are widely used as indicators of transport distance and energy, are influenced by the hardness of the grains and by the hardness of the other particles with which they come into contact during transport. Hard minerals such as quartz tend to retain angular shapes over long transport distances, while softer minerals such as calcite and feldspar are more rapidly rounded by abrasion. The sorting of sediments by grain size, which is another important indicator of depositional environment, is also influenced by hardness. As harder grains tend to be more resistant to breakage during transport and are therefore more likely to retain their original size. The study of mineral hardness, seemingly so simple and so straightforward in its basic concept, thus reveals itself upon closer examination to be a subject of considerable depth and breadth, touching upon fields as diverse as crystallography, quantum mechanics, planetary science, art history, industrial engineering, and the philosophy of measurement itself. The scratch test, that most elementary of all materials tests, which can be performed by anyone with a fingernail and a piece of rock, is at the same time a window into some of the most fundamental questions in the physical sciences. What determines the strength of the chemical bonds that hold matter together? How do the arrangements of atoms in a crystal influence its macroscopic properties? Why are some materials able to resist deformation while others yield readily under the slightest pressure? These are questions that have occupied scientists and engineers for centuries, and the study of mineral hardness, in all its forms and at all its scales, continues to provide valuable and often surprising answers. The pedagogical role of the Mohs hardness scale in geology education deserves particular mention, as it is one of the first quantitative concepts that students encounter when they begin the study of minerals and rocks. In introductory geology courses around the world, the scratch test and the Mohs scale serve as an accessible entry point into the broader science of mineralogy, introducing students to the idea that the properties of minerals can be measured, compared, and used as the basis for systematic classification. The simplicity of the Mohs scale makes it an ideal teaching tool, allowing students to gain hands-on experience with mineral identification from their very first laboratory session. The Mineral Identification Laboratory, which is a standard component of introductory geology courses at universities worldwide, typically involves the examination of a collection of mineral specimens, each of which must be identified on the basis of its physical properties, including hardness, color, luster, streak, cleavage, fracture, crystal form, and specific gravity. Of these properties, hardness is often the most useful for narrowing down the identity of an unknown mineral, because it can be determined quickly and with reasonable accuracy using nothing more than a fingernail, a coin, and a glass plate. A mineral that can be scratched by a fingernail has a Mohs hardness of less than 2.5, which limits the possibilities to talc, gypsum, and a few other soft minerals. A mineral that cannot be scratched by a glass plate has a hardness greater than 5.5, which points toward quartz, topaz, corundum, or diamond, among others. The use of hardness as a diagnostic property is particularly valuable for distinguishing between minerals that are similar in appearance, but differ in composition. Calcite and quartz, for example, are both common, light-colored minerals that can occur in transparent to translucent crystals, and they are frequently confused by beginning students. However, calcite has a Mohs hardness of 3 and is easily scratched by a copper coin, while quartz has a hardness of 7 and cannot be scratched by a steel knife. This difference in hardness provides a quick and definitive test for distinguishing between the two minerals, without the need for any specialized equipment. The extension of hardness concepts to non-mineral materials provides another avenue for pedagogical exploration. The hardness of metals and alloys, which is of central importance in metallurgy and mechanical engineering, can be related to the Mohs scale through the use of conversion tables that approximate Mohs hardness values for materials characterized by Vickers, Rockwell, or Burnell hardness numbers. Pure copper, for example, has a Vickers hardness of approximately 40 to 50 and a Mohs hardness of approximately 2.5 to 3.0. Mild steel has a Vickers hardness of approximately 120 to 150 and a Mohs hardness of approximately 4 to 5. Hardened tool steel has a Vickers hardness of approximately 600 to 900 and a Mohs hardness of approximately 6 to 7. These comparisons help to bridge the gap between the geological and engineering perspectives on hardness and to demonstrate the underlying unity of the physical principles involved. The future directions of hardness research are likely to include the continued development of computational methods for predicting hardness from first principles, the exploration of new classes of superhard materials, the application of nanomechanical testing to an ever wider range of materials and structures, and the integration of hardness data with other mechanical property data to provide a more comprehensive understanding of the mechanical behavior of materials. The development of machine learning approaches to the prediction of material hardness, in which large databases of experimental hardness data are used to train algorithms that can predict the hardness of new materials on the basis of their chemical composition and crystal structure, is an emerging area of research that holds considerable promise. The intersection of hardness science with nanotechnology has produced several intriguing developments. The mechanical properties of individual nanoparticles, nanowires, and nanotubes can differ significantly from those of the same materials in bulk form due to the effects of surface energy, reduced defect density, and quantum confinement. Carbon nanotubes, for example, have been predicted and in some cases shown to possess extraordinary mechanical properties, including tensile strengths and elastic moduli far exceeding those of any conventional material. The hardness of nanoscale structures is difficult to measure using conventional methods, and new techniques, including atomic force microscope-based indentation and in situ transmission electron microscope indentation, have been developed to address this challenge. The story of mineral hardness, told in its fullest and most unhurried form, is ultimately a story about the human desire to understand and to measure the physical world. From the first time an ancient toolmaker noticed that one stone could scratch another, to the latest theoretical calculation of the ideal hardness of a hypothetical crystal structure, the study of hardness has been motivated by a combination of practical need and intellectual curiosity that is characteristic of the best scientific work. The Mohs scale, with its 10 familiar minerals arranged in their quiet ascending order from talc to diamond, stands as a lasting monument to this tradition of careful observation and systematic inquiry. A tradition that continues to yield new insights and new applications with each passing year, as reliably and as steadily as the minerals themselves endure in the patient and unhurried geology of the earth. The specialized vocabulary that has developed around the measurement of mineral hardness reflects the discipline's long history and its roots in multiple linguistic traditions. The term hardness itself derives from the Old English herd, meaning firm or resistant to pressure, and its cognates in other Germanic languages, including the German hart, and the Dutch hard share the same fundamental meaning. The Greek word skleros, meaning hard or dry, gave rise to the term sclerometer, which is a general term for an instrument used to measure hardness, and to the related terms scleroderma, sclerosis, and sclerite, each referring to a hardening or hardened state in biological or medical contexts. The Latin durus, meaning hard or lasting, is the root of the words durability, endurance, and indurate, each of which captures a different aspect of the concept of resistance to physical alteration. The terminology of the various hardness testing methods reflects the nationalities and institutional affiliations of their developers. The Mohs scale bears the name of its creator, the German mineralogist Friedrich Mohs. The Vickers test is named after the British engineering firm Vickers Limited, in whose laboratories it was developed. The Knoop test is named after the American physicist Frederick Knoop. The Rockwell test is named after the American industrialist Stanley P. Rockwell. The Brunel test is named after the Swedish engineer Johann August Brunel. This proliferation of named scales and methods, while sometimes confusing to the uninitiated, reflects the practical reality that different materials and different applications require different testing approaches, and that no single hardness test is optimal for all purposes. The physical unit of hardness varies depending on the testing method employed. The Mohs scale, being purely ordinal, has no physical unit at all, only the dimensionless numbers from 1 to 10. The Vickers and Knoop hardness numbers are expressed in units of kilograms force per square millimeter, representing the applied load divided by the projected area of the indentation. The Brunel hardness number is similarly expressed in kilograms force per square millimeter, but it is calculated using the curved surface area of the indentation rather than the projected area. The Rockwell hardness number is dimensionless and is calculated from the net depth of the indentation according to a formula that varies with the particular Rockwell scale being used. The conversion between different hardness scales is a matter of considerable practical importance, particularly in engineering applications where specifications may be written in terms of one scale, while the available testing equipment uses a different scale. Conversion tables relating Mohs, Vickers, Knoop, Rockwell, and Brunel hardness values have been published by numerous standards organizations, including the American Society for Testing and Materials and the International Organization for Standardization. However, it should be emphasized that exact conversion between different hardness scales is not possible, because each scale measures a slightly different physical property, and because the relationship between the different measures of hardness depends on the specific material being tested. The conversion tables therefore provide only approximate equivalences, and direct measurement on the appropriate scale is always preferred when accuracy is important. The metrological aspects of hardness testing, that is, the science of ensuring that hardness measurements are accurate, reproducible, and traceable to primary standards, have been the subject of considerable attention from national metrology institutes and international standards organizations. The traceability of hardness measurements is achieved through a hierarchical system of calibration in which each hardness testing machine is periodically checked against certified reference blocks, which are in turn traceable to primary reference machines maintained by national metrology institutes. The certification of reference blocks is itself a demanding task, requiring careful control of surface preparation, indentation placement, and measurement technique. And the uncertainties associated with reference block certification place ultimate limits on the accuracy of hardness measurements in practice. The environmental dependence of hardness measurements, while generally small for most common minerals and metals, can become significant under extreme conditions or when the highest levels of accuracy are required. Temperature is the most important environmental variable, as the hardness of most materials decreases with increasing temperature due to the enhanced mobility of dislocations and other defects at elevated temperatures. Humidity can also affect hardness measurements on some materials, particularly those that are susceptible to stress corrosion or hydration. The rate at which the load is applied in an indentation test can influence the measured hardness, as some materials exhibit rate-dependent deformation behavior, known as creep, in which the material continues to deform slowly under a constant applied load. For this reason, hardness testing standards typically specify the rate of load application and the duration of the loading period to ensure that measurements made at different times and in different laboratories are comparable. The philosophical question of whether hardness is a fundamental property of matter or merely a convenient shorthand for a complex set of more fundamental properties has been debated by materials scientists and philosophers of science. On one view, hardness is not a single, well-defined physical quantity, but rather a composite property that depends on the elastic modulus, the yield strength, the work hardening rate, the fracture toughness, and the friction coefficient of the material, as well as on the geometry and material of the indenter and the details of the testing procedure. On this view, a hardness number is not a direct measurement of any fundamental property, but rather an empirical index that provides useful practical information about the mechanical behavior of a material under a specific set of testing conditions. The opposing view holds that hardness, while certainly a complex property, captures something real and meaningful about the resistance of a material to permanent deformation, and that the various hardness tests, despite their differences in detail, are all measuring fundamentally the same thing, namely the material's capacity to resist the localized plastic flow that occurs beneath a hard indenter. This philosophical debate has practical implications for the design and interpretation of hardness tests. If hardness is viewed as a fundamental property, then the goal of hardness testing is to measure that property as accurately and as reproducibly as possible. And differences between the results of different testing methods should be regarded as measurement errors to be minimized. If hardness is viewed as a composite index, then different testing methods may be expected to give different results, and the choice of method should be guided by the specific application for which the hardness data will be used. The quiet persistence of the Mohs scale, unchanged in its essentials for more than 2 centuries, in the face of far more precise and theoretically sophisticated alternatives, suggests that there is something deeply appealing about the simple idea of comparing the hardness of one material to that of another by the straightforward expedient of seeing which one can scratch the other. This appeal lies not only in the practical simplicity of the method, but also in its directness and its transparency. A scratch is a scratch, visible and undeniable, and the relative hardness of two minerals determined by the scratch test is not a matter of interpretation or statistical analysis, but of direct physical observation. In a scientific world increasingly dependent on complex instrumentation and sophisticated data analysis, the Mohs hardness test stands as a reminder that the most fundamental observations in science are often the most direct, and that the most enduring scientific frameworks are often the simplest. The industrial applications of hardness testing have expanded enormously over the past century, driven by the increasing demands of manufacturing, aerospace, automotive, and construction industries for materials with precisely controlled mechanical properties. In the steel industry, hardness testing is used at virtually every stage of production, from the initial assessment of raw materials to the final inspection of finished products. The hardness of a steel component provides a quick and reliable indication of its tensile strength, its resistance to wear, and its suitability for the intended application. For many engineering applications, the relationship between hardness and tensile strength is sufficiently well established that a hardness test can serve as a surrogate for the more time-consuming and destructive tensile test. The heat treatment of steel, which involves controlled heating and cooling to produce desired microstructural changes and mechanical properties, is routinely monitored and verified by hardness testing. The quenching of austenitic steel to produce martensite, a hard and brittle phase, can increase the Rockwell C hardness of a medium carbon steel from approximately 20 to approximately 60, corresponding to a Vickers hardness increase from approximately 230 to approximately 700. The subsequent tempering of the martensite, which involves reheating to a moderate temperature to reduce brittleness while retaining most of the hardness, produces a controlled decrease in hardness that is predictable from the tempering temperature and time. The relationship between tempering conditions and hardness has been extensively studied and tabulated for a wide range of steel compositions, and hardness testing is the standard method for verifying that a heat-treated steel component has achieved the specified properties. The hardness of ceramics, which are generally much harder than metals, but also much more brittle, is measured using the same indentation techniques that are applied to metals, with appropriate modifications to account for the different deformation mechanisms. In metals, indentation produces predominantly plastic deformation, with dislocations moving through the crystal lattice to accommodate the shape change caused by the indenter. In ceramics, which have limited dislocation mobility, indentation produces a complex zone of deformation that includes both plastic flow, often accommodated by twinning or phase transformation rather than dislocation motion, and radial cracking that emanates from the corners of the indentation. The lengths of these radial cracks can be used to estimate the fracture toughness of the ceramic, providing additional information about the mechanical behavior of the material that goes beyond the simple hardness number. The hardness of polymers and other soft materials presents its own set of challenges, as these materials often exhibit time-dependent deformation behavior that can affect the measured hardness. The Shore durometer, developed by Albert Ferdinand Shore in the 1920s, is the most widely used method for measuring the hardness of polymers, elastomers, and other soft materials. The Shore durometer uses a spring-loaded indenter that is pressed into the surface of the material, and the hardness is determined from the depth of penetration under a standard load. Two scales are commonly used. The Shore scale, which uses a truncated cone indenter and a lighter spring, is used for softer materials such as rubber and flexible plastics. The Shore D scale, which uses a sharper conical indenter and a heavier spring, is used for harder materials such as rigid plastics and hard rubber. The measurement of hardness in thin films and surface coatings requires specialized techniques that can distinguish between the properties of the coating and those of the underlying substrate. When a conventional hardness test is performed on a coated surface, the measured hardness is a composite value that depends on both the coating and the substrate, with the relative contributions depending on the depth of the indentation relative to the thickness of the coating. A general rule of thumb is that the indentation depth should not exceed approximately 10% of the coating thickness if the measured hardness is to be representative of the coating alone. For very thin coatings, which may be only a few hundred nanometers thick, this requirement limits the indentation depth to a few tens of nanometers, placing the measurement firmly in the domain of nanoindentation. The development of continuous stiffness measurement techniques in nanoindentation, in which a small oscillatory force is superimposed on the monotonically increasing loading force, has made it possible to measure the hardness and elastic modulus of a material as a continuous function of indentation depth during a single test. This capability is particularly valuable for the characterization of graded coatings, in which the composition and properties vary continuously with depth, and for the identification of depth-dependent deformation mechanisms. The continuous stiffness measurement technique was developed in the late 1980s and early 1990s, and it has since become a standard feature of most commercial nanoindentation instruments. The role of mineral hardness in forensic science, while less widely known than its applications in geology and engineering, is nonetheless significant. The analysis of soil and mineral particles found at crime scenes, on clothing, or on tools can provide valuable evidence linking a suspect to a particular location or activity. The hardness of mineral particles can help to identify the geological formation from which they originated, and the pattern of wear on tools and surfaces can provide information about the hardness of the materials with which they have been in contact. Forensic geologists, who specialize in the analysis of geological evidence in legal proceedings, routinely use hardness testing as one of several diagnostic methods for identifying mineral particles and reconstructing the circumstances of crimes. The application of hardness concepts to the study of ice and frozen materials is another specialized area that has implications for fields as diverse as glaciology, food science, and cryogenic engineering. Water ice, in its most common hexagonal crystalline form known as ice, has a Mohs hardness that varies with temperature, ranging from approximately 1.5 at just below the melting point of 0 degrees Celsius to approximately 6 at -70 degrees Celsius. At the extremely cold temperatures found on the surfaces of the outer planets and their moons, water ice behaves mechanically much like a hard rock, and the geological features observed on these bodies, including craters, ridges, and fracture systems, are shaped by the mechanical properties of ice at these temperatures. The hardness of frozen soils and permafrost is of considerable practical importance in the construction and maintenance of infrastructure in Arctic and subarctic regions. Frozen soil is a composite material consisting of mineral particles, ice, and air, and its hardness depends on the relative proportions of these components, the temperature, and the grain size distribution of the soil. The penetration resistance of frozen ground, which is a measure related to hardness, is used by engineers to assess the difficulty of excavation and to design foundations for buildings, pipelines, and other structures in permafrost regions. The thawing of permafrost due to climate change is causing significant softening of previously hard frozen ground, leading to the subsidence and damage of buildings and infrastructure across large areas of the Arctic. The hardness of materials under dynamic loading conditions, in which the load is applied rapidly rather than quasi-statically, can differ significantly from the hardness measured under the slow loading conditions of conventional tests. Impact hardness, which is the resistance of a material to deformation under a rapidly applied load, is measured by methods such as the Charpy and ISID impact tests, in which a pendulum or falling weight strikes a notched specimen and the energy absorbed in fracturing the specimen is measured. While these tests measure toughness rather than hardness in the strict sense, they provide complementary information about the mechanical behavior of materials under conditions that are more representative of many real-world applications, such as impacts, collisions, and explosions. The comprehensive study of mineral hardness, encompassing as it does the atomic scale mechanisms of crystal deformation, the macroscopic mechanics of indentation and scratch testing, the geological processes of mineral formation and weathering, and the industrial applications of hard materials and hardness testing, provides a uniquely integrative perspective on the physical properties of the solid materials that make up the Earth and that form the basis of so much of human technology. The Mohs scale, that deceptively simple ranking of 10 common minerals, serves as the entry point to this vast and fascinating subject, and its enduring usefulness, more than 2 centuries after its creation, is a tribute to the power of careful observation and systematic classification in the advancement of scientific understanding. The minerals continue to scratch and resist in their patient, unhurried way, and the scientists and engineers who study them continue to find, In these simple interactions between hard surfaces, a wealth of information about the fundamental nature of matter and the remarkable diversity of the material world